Okay, today we're going to cover probably, I think for many of you in this room, the most valuable concepts from this entire course. That's not to say that the free energy, the corrosion, electrochemistry, all that isn't important, but I think especially for the mechanical engineers where you're designing components and you need to make sure that they work and that they don't fail within some percentage, this will be certainly the most valuable thing that we're going to cover. So today, here's our learning objectives. We're going to first talk about how we deal with variability in test data. We're then going to use Weibull probabilistic failure statistics to determine what stresses might cause an arbitrary failure or success rate when subjected to a given stress condition. So let's first talk about variability. So even if you have the same sample, and even if you perform the experiments very, very carefully, you're not always going to get 100% of the time the same values. There's always variability. Some of this might be due to operator bias. It might be your sample calibration. It's certainly going to be related to specimen fabrication, and there can be other factors. So for example, this can be for anything. If we had rubber bands and we took the rubber band and we stretched it until the point where it broke, the distance that we could stretch it, so the elongation up until failure, will not be the exact same. We're going to get a bunch of values, right? Another thing we could do, what if you took a rubber band and you stretched it and you determined how long could you hold it until it broke or until it reached some, stress relaxation that we're going to call failure. Again, it's going to be some distribution. You could do this with many, many things. Obviously, strength of samples. If you order some steel plate and you make dog bones out of it and you test their strength, they're not all going to yield or fail at the same, stresses. There's going to be some distribution. Now, that distribution may be broad and it may be narrow. Like, for example, if this is the number of samples and this is stress, you might have a distribution that looks like the following. It might be really narrow, or you might have one that's really broad, right? The broad one might have a slightly higher average value than the blue one. But the blue one, even though it's weaker on average, has a much tighter distribution. So a good question to ask is, as engineers, what do we do with this? Do we prefer one of these materials over the other? And how do we deal with scattering the data? How do we talk about it? Because it's going to be important. So there's a couple things. And maybe this is a good way to frame the question for today is, which of these phrases is more useful? What is the yield strength of this alloy? And that's what a lot of us use. We look up in the back of the book in the appendix, we look up on spec sheets, and we look up the yield strength. And that represents an average, right? So how about this question then? Instead of the first one, what if we did this? What is the probability of yielding for this alloy under these conditions? Which one of these is more useful? Definitely the second, right? Because now it's probability. Now we can say for some applications, maybe 10% failure or 10% yielding is acceptable, but maybe you need to have 1 in 10 million fail or yield, right? So this is much better because now it's talking about probabilities. So to get started, let's first talk about average values. An average, I'm sure you would have seen this in math at some point, but average, we'll call it X with a bar on top. That means the mean or the average value is calculated by summing up each individual value, xi, and you go from I equals 1 all the way up to however many samples you have. You add all these up, so the summation, and then you divide it by the number of samples, right? So if you have 10 samples, you'd figure out what those 10 values were, you divide it by 10, and that's your average. That's useful, an average value is certainly useful, but it doesn't tell the whole story because it doesn't tell you how broad, like the red sample here, or how narrow, like the blue data is, right? It doesn't tell you that. So one thing that is commonly reported is standard deviation. Now, standard deviation can be written as, you're gonna, in the numerator here, inside of this square root function, the numerator is the sum of this in parentheses squared. This whole thing right here, that's called the variance. Variance is just equal to the individual value x, of some compound, so some value minus the average value, and you take that difference and you square it. That's the variance. So you're going to add up the variance and you're going to divide it by the number of samples minus 1 and take this all to the 1/2 power. That is by definition standard deviation, and there's actually different types of standard deviation. That's one of them that is commonly used, right? So if you had a normal distribution or a bell curve, then a standard deviation can be kind of a useful value because it tells you how much of your sample population lies within the standard deviation. For example, if this is your average value here, right here, then within plus or minus 1 standard deviation, right, we know that that encompasses 34.13% times 2. So 68.2% of your total sample population lies within 1 standard deviation. So now you're not only reporting the average, the 50% value, but you're saying from that average, roughly 2/3 of your total sample population is captured within this plus or minus, right? So that's actually becomes kind of useful. And then if you do 2 standard deviations, you go out 2, now you've captured 95.6. If you go out 3 standard deviations, you've captured 99.8. So by the time you're at 3 standard deviations, that's pretty good. You're saying essentially almost all of your sample is captured within that value, which is it's a good measure of how dispersed or how much scatter there is in your data. In fact, you can keep on going out. 6 sigma, many of you might have heard this, especially if you're working in industry already, because a lot of industries use this. 6 sigma means if you go out plus or minus 6 standard deviations, you will have captured 99.99966% of your sample population. And so this is useful if you need to really carefully control the number of defects produced. So if you want to yield, whether it's iPhones or Toyota Camrys or whatever else, and you want to have a very high yield of high quality products, 6 sigma is something that's been introduced. So it was actually started in Motorola in 1986, and it gained popularity, and eventually Jack Welch, the CEO of General Electric, really adopted it as one of their core strategies for manufacturing everything that they make. And basically it allows you to have a very, very high yield because only 3.4 defects are present per million samples if you've achieved 6 sigma. So it's a way of manufacturing where you figure out what's the thing that's causing us to have our largest failure. You identify it, you fix it, you change that processing or those components or whatever it was, and then you find out what's the next thing that's causing the most failures. You do this until you have 6 sigma yield. Right? So that's important. Many of you that go on to get jobs will probably actually get certified in 6 sigma. They actually call it 6 sigma black belt, and there's these training courses for it. We don't offer that in our department. Next up, as engineers, a lot of you will actually probably just use design or safety factors. This actually, unfortunately, is what a lot of times is used. And this can be thought of in 2 ways. First off, we say, all right, the design stress is going to be based off of an expected stress level, and then we're just going to multiply that expected stress level by some design factor, right? So if you think that, you did the design, or when you calculated it, you said, okay, well, there's probably going to be 100 megapascals that this component is going to actually observe. So let's multiply it by some safety factor or design factor, maybe 2 or 3 or 4, and let's design it for a much larger stress than we think it's actually going to observe. So this can be thought of as over-engineering. And again, that factor N is just picked based off of past experience, gut feelings, right? Not very quantitative measures. And the other way this is sometimes done is they think about it in terms of safety stress or working stress based off the yield stress. So let's say your alloy has a yield stress. For example, aluminum tensile strength is about 50 megapascals. So instead of designing for 50 megapascals, they say, let's do that divided by some factor, N, right? So we're not going to load it up in our design. We're not going to design it to take 50 megapascals because that's when it would break. Instead, we're going to do it divided by some factor, 2 or 3 or 10 or something, right? And so this can be thought of not as over-engineering, but rather as assume worse performance. The spec sheet says that your alloy is good to some value. Assume that it's going to be worse by some safety factor. So these are certainly better than nothing, but these will not tell you, hey, I have to design this component to survive 1 in a million. We only want 1 failure per million samples made. This just won't do it. This won't cut it, right? It's not quantitative. So instead, we really need to move from this gut feeling sort of design and safety factors towards a quantitative, probabilistic failure analysis, and that's where Weibull modulus comes in, which I think will be one of the more valuable things we're going to talk about in this class. So Weibull modulus was invented back in the 50s by a Swedish mathematician, Walody Weibull, and he basically said, all right, if we come up with an expression that more or less fits data, assuming different types of data, not always necessarily normal, right, but it's going to be some scattered data, something like we drew before, again, where the number of samples that fails at given stresses, you don't have very many that fail at low values. You can have some at some average value, and then you have some that actually survive up to very high stresses they might survive out to, right? So he says, all right, if you have that, you can write an expression where F is your probability of failure, and f will equal 1 minus exponent of negative sigma f. That's going to be your characteristic strength. That's the strength. That's the strength at failure, right? You're going to divide that by a characteristic strength, sigma naught. That's just going to be a fitting or a scaling parameter. And you're going to raise it to the m, and that's the Weibull modulus. And if you do this, you can fit a lot of data with just these two parameters, m and sigma naught, right? You can fit a lot of data. Therefore, f equals 0.5. That corresponds to an average strength, or 50% failure, right? So what's clever about this is that it allows us to calculate sigma naught and m very evenly, and then we can start making probabilistic predictions of performance if we test enough samples. Here's how it works. Consider this original expression. We're going to reformulate it just a little bit. I'm going to bring the exponent to one side by itself, and I'm going to bring f over by itself. So now we have 1 over 1 minus f equals exponent of, note the positive here, positive sigma f over sigma naught to the m. We got rid of the negative sign, right, by switching it, by taking 1 over, okay? Now if we take natural log of both sides, we get rid of the exponent. So we have natural log on this side, and we have just what was inside the exponent before. And if we take natural log one more time, we've got natural log of 1 over 1 minus f equals m. M's able to be brought down, m times natural log of what was in the numerator here, natural log of sigma f. And since this was a division, when you take natural log of that, we can rewrite that as minus m times natural log of sigma naught. So why on earth did we do this? That seemed a bit arbitrary. We do it for a reason. All of a sudden, this whole thing, we're going to call that y. We're going to say that, let's see, this is b. This is going to be mx, and this is going to be b, right? So all of a sudden we can make a complicated plot that looks like this. We can turn it into something that looks linear, right? All we need to know is what is the fraction of components that fail at a given stress, right? I'll show you how to do that in just a moment. And we can calculate this, and then we can do probabilistic analysis with it. So m is the Weibull modulus. Natural log of, let's actually separate this to be a little clearer. Natural log of your failure stress is going to be your x value, and this whole term is going to be b, right? So let's do, one more thing here. Weibull modulus m, a large Weibull modulus is desirable because that means that there's less spread in the failure data. So for example, if we go back here to the two plots we saw, this one that had a very low spread, they were all pretty narrowly clumped together, that would have a higher Weibull modulus than the red data set, which would have a lower Weibull modulus. Generally, it's very desirable to have a low spread because it's easier to design around it. I'll show you why in just a moment. Okay. So how do we get this f value? If we're going to plot this whole thing and make that the y-axis, where do we get f from? Well, there's a number of different ways to determine f. It's technically the failure probability, but to calculate it, perfectly, you'd have to test infinitely many samples and figure out where things failed. What's the percent in which it failed at a given stress? There's a better way to do it. Here's what we do. We rank the samples in order of failure, right? So maybe you had a sample that broke at 5 megapascals, one broke at 10, one broke at 3, one broke at 20, one broke at 25, and so forth, right? We're going to rank these. So we'd say they went like this: 3, 5, 10, 20, 25. So this was the first, this was the second, this is the third, fourth, fifth, and so on. And typically you have large sample populations. A good rule of thumb is that you need at least 20 samples. You need at least 20 samples to do decent Weibull modulus analysis. Right? More is always better, and the more you do, the better your confidence interval, which we won't really talk about in this class, but more is always better with this. But 20 is a good rule of thumb, right? So you rank them from lowest to highest, right? And then you can calculate f by doing the following. F is going to equal n minus 0.5, where n is the nth order of failure. So for example, for this component right here, n would be equal to 2. It's the second sample that failed, the second lowest strength. So it would be n minus 0.5 divided by big N, which is the total number of samples, which in this case would be 5. And remember that generally for Weibull modulus, we want at least 20 samples for big N, right? So once you do that, you can calculate F for each one of these samples. Now let's actually see some data. I think this is easier to see with actual data. So here we have an example. I've got some bar IDs. Let's say you tested 35 bars, right? From A1 to A35. You tested these bars. And let's assume that you have two different type of bars, one of which produced a tight distribution but was weaker, and the other one had a broader distribution but was stronger. So for this one, I'm having it randomly generate a number between 200 and 500, right? Here I'm having it generate randomly a number between 300 and 900, and I'm multiplying that by a random number between 1 and 3, right? So it's going to generate these. So the first thing we need to do is we need to rank these. So let's take these two expressions, these two columns, right? We're going to take them, let's copy them, and let's paste them here we're going to do paste special, and we're just going to paste values. Right? So just the values. And as soon as I do that, these have changed, right? Because it randomly updates every time you do this. So right now, these are not ranked in order, right? This one failed at 308, but we want the highest ranked one, 1698, but there's higher ones, like 26. So how do we do this? So you would highlight this whole column, right click it and go to sort, and you're going to sort from the smallest to largest. And then importantly, we do not want to expand the selection. We just want to sort in that small column we have right there, right? Let's do the same thing for our broad but strong. Sort them. Oh, oops. You can also do it with hotkeys. Sort, smallest to largest. Again, we only want that selection, don't expand it. Okay, now if we go down here, we can see that this data set here, I've plotted just a histogram of the data. I've plotted both these data sets. You can see, in fact, that the blue, it fails at lower values. This is just number of samples versus the strength at which it failed, for example. It is much tighter, but it's lower. The orange is much broader, and it's higher on average, okay? So for both of these data sets, now that they're ranked, we can calculate F for them. F is our failure probability. So again, if you look up here in the formula box, we have our rank of failure, E2, minus 1/2, divided by 35, since we have 35 samples. And you do this all the way down, right? All the way down like this. So somewhere in the middle, right? Between 1 and 35, the average is somewhere around 17. I guess it'll be 18 here, right? So between 17 and 18. This should give us 50% failure, right in the middle, right? 50% of the samples failed below, and 50% of the samples failed at higher values. And sure enough, F gives us about 0.5. Now, it's not exactly right, because remember, we're doing this minus 1/2. If you tested infinitely many samples, it's going to get better and better. But this is a pretty good approximation for our failure probability. So this means if they took, for the weak samples, right, and you loaded it up to 495 megapascals, right, then you would have 95% of your samples fail. The only one that wouldn't fail would be this one, right? Similarly, if you took and loaded up to 1565 for the broad and strong samples, 1565, you'd have 70% of your samples. All these ones would have failed below it, and all the ones above that would have survived, right? So now we have F. So going back to our expression here, we want to take natural log of 1 over 1 minus F, and we're going to call that whole thing Y. So over here, that's what we have. I've taken natural log of 1 divided by 1 minus H2, which is our F value, right? So we've got that. So it's just a bunch of values, right? All the way down we did that for all these samples. Now, if we want to plot this, we also need to plot that Y against X. And our X needs to be the natural log of whatever our failure criteria is. In this case, it's strength, right? So here we have natural log of the strength at which it failed, right? So plotting, this is going to be the X column for the weak data, and this will be the Y column that we're going to plot, and then this will be the X column for the strong samples, and this will be the Y column. When we do that and plot it, here's what we get. Let me make this a little bigger. This is a Weibull plot. Again, on the y-axis, natural log of 1 over the quantity of 1 minus f. On the x-axis, we just have the natural log of sigma f. So this is natural log of whatever our strength of failures for an individual component. And you can see that these now look linear. They should look linear because we assumed that we had a distribution that could be more or less be fit by this Weibull expression here, right? And not all of them can, but many can. So it's roughly linear. It's not perfect. You can see the r squared value is 0.95 and 0.95 for both of these. Pretty good. And now we have a y equals mx plus b for both of these, right? So from these, we immediately know that the orange data set, which we said is this one, that's our weak data set, which we designed it to be a tighter data set. In fact, it has a higher Weibull modulus, 5.039, then the other data set right here, which was our strong data, it has a fitting parameter. The slope is 2.16, so it has its Weibull modulus is lower. So which one is better? Now we can actually start answering that question, because at some point these lines are going to intersect, right? They're going to intersect somewhere around here, and at that point, this one, if you're talking about failures in that regime, you might actually prefer the on average weaker sample because that's a tighter distribution. We'll do an example in a moment. Okay, so that is how you do this. You'll have an example of it on the next homework, how you do Weibull calculations. Let's talk a little bit more about it. Okay, you get this linear fit. From the linear fit, you get a y equals mx plus b, and that allows you to calculate Weibull modulus, and the characteristic strength is just a fitting parameter. So some more things we can take from this. Let's say that for this material here, let's say for the blue material, for the blue data set, we want to design it. We want to know what stress we can load our component to such that we will only have one failure per million samples, right? We only want one failure. So we want, a very, very high fraction of these things to survive. So what is that fraction? What's the fraction of failure that we want? We only want, let's write it out on our sheet here. Let's say if we want only one sample in a million to fail, what stress should we subject our component to? Right? This is now probabilistic. So how do we do this? We're going to say, all right, we want 1 over 1 times 10 to the 6th to be equal to f. Right? 1 in a million. We want that to be our failure criteria, right? And now that you've got f, if you take that, it's going to be equal to 1 times 10 to the negative 6th, right? Then we can plug that into natural log of 1 over 1 minus f, and we can get a value, right? It's going to equal a number. Let's calculate it really quick and see what that value is. So natural log of 1 divided by the quantity of 1 minus 1e to the negative 6. Make sure I've got all the parentheses. I get that equals negative 13.8155. So that will be our y-axis, right? So we go back to our data and we say, all right, this only goes to negative 5, right? But you could extend it all the way down. You could go down, to negative 13.85, and you would see basically at what value that corresponds for these things, right? We have to replot this so you can see where it would intersect it. Or you can just do it mathematically, right? You can say, well, I know what these expressions are. Let's do it for the blue data set. The y equals mx plus b is as follows, right? It's this thing. Let's just grab it. Let's grab that. Right, that's our data. Let's make that a little bit bigger to see it easily. Okay, that's our y equals mx plus b. And y, recall that y equals natural log of 1 divided by the quantity of 1 minus f, right? So we have y already. Now we have the expression for this, so we can plug in at what x that corresponds to. So we just need to solve for x. So let's do so. Now that we know what y is, we're basically going to set up this equation, the following equation. We're going to say, oops, excuse me. We're going to say, all right, negative 13.8155. That needs to be set equal to to 2.1602 x minus 15.595, right? So now we can solve for x. When we solve for x, I get that it is equal to I get that x is equal to 0.823. 0.8237. So does that mean that we can only load it up to 0.8237 megapascals? No, because X does not equal strength directly. Recall what X equals. If we go back up here, X was equal to natural log of the strength. So we say, all right, natural log of our strength, where 1 in a million is going to fail, is equal to 0.8237. Therefore, the strength at which 1 in a million samples will fail is equal to exponential, this term, 2.27. 2.279, right? So basically, if you really want 1 in a million samples to fail, and you can't have any more than that, then for our blue data set, which was the stronger one, you can't go above that stress, right? Or technically, you're going to have more than 1 sample in a million fail. But let's look at our other data set, right? The other data set was right here, the orange data set. This, on average, was weaker, but it had a tighter distribution. So let's plug in its values here. Let's grab these. Come back over here, let's paste them, right? Again, make it big enough to see. Okay, we're going to do the same thing. F is the same as before. We calculate F the exact same way. So we can just say that negative 13.812, I think that's what it was. Negative 8155 is going to now be equal to 5.039 x minus 30.032, right? Now when we solve for x in this scenario, x is going to equal x equals now 3.218. 3.2182. Therefore, natural log of the strength of failure for 1 in a million to fail is 3.2182. And finally, give ourselves a little more room. We find that the strength of failure for 1 in a million to fail, meaning almost all of them survive, for this component is going to be natural log of 3.2181, which is 24.98. And this is pretty awesome. So consider this. We started out with 2 distributions, right? We had our weak but tight distribution right here, and we had our broad and strong distribution. Now, as an engineer, looking at these numbers at which they fail, it's pretty obvious that most people, I think, before they had an understanding of Weibull modulus, they'd say, oh, let's use the broad and strong. Like, look how much higher the average strength is. It's huge, right? Average strength here is 355, here it's 1100. But by taking into account the scatter, meaning the distribution, which it comes from understanding Weibull modulus, all of a sudden we can understand that if you need 1 in a million samples to fail only, all of a sudden it's actually better to use the tight and weak distribution. And we can probabilistically figure that out with this approach, which is a very powerful tool. But it gets even better, right? So, let's see, we can skip this part. Let's get to this end part right here. How do we actually use this as engineers? Well, it's fine if you're testing bars, right? If you're testing little matchstick shaped pieces of ceramic or whatever, it's fine to test it for that. But in the real world, we're building objects. We're building beakers, we're building bearings, we're building drive shafts, we're building all sorts of things. And what's amazing and terrific about this is that Weibull analysis allows us to scale for larger and larger components, which we know will have statistically higher odds of having that critical flaw that will cause it to have failure. Therefore, we have this handy expression. This says the following. It says, the strength at which a component will fail can be calculated from the strength at which a bar failed using the Weibull analysis when you take into account the effective area of the bar divided by the effective area of the component raised to the 1 over m value, where m is Weibull modulus. What does that mean? Let's say we calculate a strength associated with some failure probability, 50%, 1 in a million, etc., right? That's all done on a bar in a lab, and that's very easy to do on small things. But you're not going to go out and build, 20 giant freeway columns and break all of those to figure out it, right? But what's great is that we can extrapolate the data from small samples like bars, our test samples, and we can extrapolate out to much larger components using this expression, right? So the same strength, or the same failure probability that we calculate here, we will have the same failure probability here in the component if we take into account the Weibull modulus and the difference in effective area. So this all of a sudden becomes very, very powerful. Calculating effective area can be a little bit tricky. We're not going to go over it in this class. Instead, on the homework, I'll give you just some expressions that you can use to calculate it. But it's not. It's definitely not undoable, and this is a great way to scale something that's done on. It's very easy to test 20 small bars to get your Weibull modulus and your expression for your Weibull analysis. But then what's amazing, you can then translate that into axle shafts on cars, and you'll be able to say quantitatively and probabilistically what is our rate of failure if we extend this out to a much larger component. And that's great because then you can design cars that hey, only 3 in a million or only 5 in a million or whatever the number is are going to fail. Or maybe you want to go the other way. You say, we need this component to fail 99.9% of the time. Maybe it's like a safety release valve and you need that component to fail in order to release pressure or something from a pressure vessel. You can figure out what fraction of the time it's going to fail and do its job correctly at a given stress. So this is a much more powerful way to think about scattering the data than simply using our gut, going off of your gut feeling and using design and safety factors. So expect an awesome homework problem on this. You're going to learn a lot when you go through it, and I think that this will be one of the more valuable things that we've learned in this class. Okay, that's all for today.